Hello everyone, we are presenting our project for 607. Our project is image classification for Amazon products. We have three members for this project. My name is Yang, and we also have Stu and Sneha. So now I'm going to pass this to Stu to talk about image scraping and cleaning.
Thanks very much, Young. So the first stage in this project was to go and get all the images off of Amazon pages for that search. So you'd look up a product and you get a return of all the different products, and we were scraping all the different images for each of those products. So we built this scraper using Beautiful Soup, and it worked quite well to grab a few images at a time, but ultimately to speed up this process and grab multiple images across multiple different pages simultaneously, we also implemented multi-threading. So after we pulled all those images, we were left with a bunch of the URLs for each of these images. So then we had to download each of these images too and save them locally. So multi-threading was also applied here so that all the images could be downloaded much faster and saved to local folders. These local folders were named as the product. So for instance, if the product search was shoes, the folder that image would be put in would be under the shoe folder. So at this point, we have a bunch of different folders. We have 11 different categories, and we had to go through and try and clean up some of these images. And we realized that because we'd pulled images from different Amazon sites, such as Amazon US, Amazon UK, to try and get as many different images as possible, we ended up having a few duplicate images. And as well, our scraper ultimately did pull some images that were undesired. For instance, if you looked up the word bike, instead of getting the image of a bike, it might be a book with the title bike. So we had to pull out those images. And what actually ended up happening was going through each of the images that we pulled and just double checking on a quick glance manually to make sure that there was nothing there and that we didn't have any undesired images in our data set. So that was quite a tedious process. And then because we'd pulled images from multiple different Amazon sites, we realized that there were some duplicates. But luckily, because of file convention, we were able to get rid of quite a few of these fairly easily. And Yang will be able to touch on this a little bit more. Having gone through now and removed any undesired images from our data set, as well as gotten rid of some of the duplicates that may have existed, we decided to do some image augmentation to try and increase the number of images in our data set that we were able to use to train our models. And we did this by shifting the original image around 9 different orientations around the screen. So ultimately, after augmentation, we ended up with around 100,000 different images across our 11 classes.
After we get the data, we need to do data pre-processing. This is important because in terms of model accuracy, also to reduce the computational demanding and also to meet the model requirement. There are 4 major steps. The first is duplicate removal. When we scrape data from different countries of Amazon, it is inevitable that some images are identical. Fortunately, when the images are same or identical, the name conventions are pretty much the same. So we can leverage these ideas in our code to remove duplicates. And then after that, we also removed colors. As you can see on the first to second image, we don't really need this color to distinguish one product versus another one. So we decided to remove that. And also the image comes with different size, different resolution. So we resize them to 150 by 150 for all the images. And lastly is the normalization. This is to maintain the image pixels within the uniform distribution. We basically divide all the values by 255, which is the total color values. And after that, we have these 11 categories with images pre-processed. We divide our classification models into 2 different sections. The first is the classical machine learning models using scikit-learn. Specifically, we have logistic regression, k-nearest neighbors, Gaussian naive Bayes, support vector machine, and trees, and PCA on top of these models as well. And on the neural network side, we choose CNN, convolutional neural network, and then the MLP, the multi-layer perceptron as well. So we have 3 leading questions. The first one is to compare the machine learning models and neural network for image classification. And we're also curious to see the effects of dimensional reduction using PCA. And then lastly, we will come to a final best suit models for tagging images for Amazon products. And now I'm going to pass this to Sneha to talk about question 1.
The first thing we want to look at is how conventional machine learning techniques compare to the neural networks for image analysis and classification. We have tried a bunch of models. The first one is logistic regression, which resulted in 64% accuracy with its best parameters as default, which we found using randomized search CV. So we fit the model with all default values and compute the score 5 consecutive times with different splits each time. Because our samples are balanced across target classes, hence the accuracy and the F1 score are almost equal. We go with the best parameters as default because the accuracy isn't that bad, and also it's expensive to train the model with its perfect parameters. Upon analysis, we found a bunch of images which were misclassified. The one that stood out was the speaker, whose value is 0.37, as we can see in the confusion matrix. The classifier often confuses it with hat or earbuds, as the packaging of earbuds resemble a container and so the speaker. Next, we tried trees, that is decision tree classifier. It has a parameter called maximum depth, that is the number of splits required. More the number of splits, the more information is captured. For large depth values, the model overfits, as we can see. So for now, we've used 10 as maximum depth value. For parameter criteria, we plotted training and test accuracy graphs for both Gini and Entropy. Not much difference though, but Gini performs at 59% accuracy. Following the same pattern for misclassification, speakers continue to be the most misclassified by trays as well, in comparison with hats and earbuds. We also tried backing classification, but it's too expensive to run them. Now we look at random forest, which probably performed the best with 76% accuracy amongst all the machine learning models. Using randomized search CV for hyperparameter tuning, which includes the number of decision trees in the forest, the number of features considered by each tree when splitting a node, and the maximum number of levels in tree. It's obvious that this accuracy is uptake in all different categories. The misclassification images still have some similar patterns as logistic regression and decision tree classifier. Random forest classifier still has hard time to distinguish speaker and earbuds. The next model we tried was SVM, support vector machines. These are also used for image classifications. We used grid search CV for best parameters as shown and got 67% accuracy, which isn't that bad. The best parameters gamma defines the impact of single training sample on the biases of the result, while C tells the cost for misclassification. The more C, higher the cost. And in our case, it's higher. The best kernel function we got is RBF, which is radial basis function. The classification of speaker improves for this model, as we can see. The last machine learning model is K nearest neighbors. The training and testing accuracy graph says that if the neighbor's value is less, it's more accurate. Although for optimization of other parameters, we choose n neighbors as 3, and it performs at 65% accuracy. So I tested for one image as shown, and it correctly classifies this image as hat. From the confusion matrix, as we see that for the class speaker, the value of it has improved with KNN. And now Yong will talk about the neural network classification for image analysis.
After trying many machine learning models, we also want to use neural network. The convolutional neural network is a canonical method when it comes to image classification. The final accuracy that we got is 77%, which is even a little bit higher than random forest, the best one. We used a random search class validation to choose the best parameters. We first built our base neural network with 9 hidden layers, which has convolutional 2D and max pooling 2D. And the learning rate for the Adam optimizer is 10 to minus 3, and the activation function is 10H. The epoch is 20. As you can see, as the epoch goes up, the blue line, the training accuracy goes up very quickly, up to 1 probably eventually. While the validation accuracy stays pretty much the same, it's about 70%, which may indicate on overfitting. If given more time, we will probably add drop out layers in between. And then the bottom here is the confusion matrix. It's pretty much the same as you see in the machine learning models. This model has also hard time to distinguish the speaker and the earbuds between among other product items. So we also tried the multi-layer perceptron, MLP. and the final accuracy is 65%. And the best parameter is that we only need one hidden layer, but we need a lot of neurons, 150, and the learning rate is the same. One interesting thing I want to point out here is this red line is the validation accuracy, which is actually higher than the blue line, which is the training data set. This is because we add the hidden, the dropout in the input layers. And then for the confusion matrix, it's pretty much the same. This model also has a hard time to distinguish speaker and earbuds among other product items.
The second question that we had looked at what the effects were of using dimensionality reduction techniques for image classification. So we applied dimensionality reduction using PCA, and I'll first talk about random forest with PCA. So when we applied PCA to our data, we ultimately retained around 25 components, which accounted for about 70% of the variance. And the way that we went about determining 25 was just through trial and error. So reducing the number of components in the data while still retaining a high accuracy with the model. So even reducing to 25 components, we still had about a 74% accuracy with this model. But from the original runtime using the full dimensionality of the data compared to the dimensionally reduced data, we went from a runtime of the model from between 40 seconds to a minute to around 13 seconds runtime. So it sped up the classification significantly while still retaining high accuracy. Now, just looking at our accuracies and the confusion matrix for the random forest using PCA, we can see that even after reducing the number of principal components in the data, we were still approaching on some overfitting. The validation accuracy was a fair bit lower than the training, and the training seems to be approaching 1. So we'd want to go and reduce the dimensions of the data further or consider other methods in trying to prevent overfitting here. But even using PCA on this data, we are still seeing some similar trends to what was touched on previously, with speakers and earbuds especially being the most difficult for our models to classify. We also want to explore the effects of dimensionality reduction on a neural network. Since CNN takes a matrix as an input, whereas MLP takes a vector of input features, we chose to apply PCA with MLP just because of this compatibility. So using cross-validation, we ultimately reduced the dimensionality of our data down to 10 components, which accounted for about 60% of the variance. And ultimately, we were able to achieve a 64% accuracy on this model with about 32-second runtime. So again, the speed at which this model is able to run at and to perform classification was increased significantly. So just on the left here, you can see which were the best parameters that were determined to build this model, and this was done again with random search cross-validation. So the number of principal components was determined to be 10. The layers in the model actually was increased to 2. Learning rate was 0.001, epochs were 20, batch size 32, and the activation was 10H. So when we look at the training accuracy versus validation accuracy, we're able to see actually that we had higher validation accuracy than training, up to about 10 epochs, and then they were pretty closely matched. So this was a good sign that overfitting likely wasn't really an issue here, but ultimately that we weren't able to get quite as high as accuracy as maybe compared to CNN. But recall with CNN, we were seeing signs of overfitting. So we'd have to do some further exploration here with this model to try and determine a little higher accuracy. So finally, for our third question, we want to conclude which are the best models to use for image classification of our 11 Amazon products. Ultimately, the models that we had which performed the best was the random forest as well as the CNN. So just to highlight some of the difference here between these two models, random forest was 76% accurate with about a 45-second runtime, whereas CNN was around 77% accurate with a 400-minute runtime. So these models run very differently, and there are pros and cons to each. With the CNN, there's definitely some further work that can be done as far as possible layer reduction, so reducing the number of layers in the model to try and shorten either the runtime or to prevent some of the overfitting that we were seeing. And then for random forest as well, there could be some additional work too, as we saw with PCA, to possibly reduce some of the components in the data to reduce some of the overfitting and possibly speed up the runtime. So ultimately, in conclusion, these were our two models which achieved the highest accuracy for classifying our Amazon images. Here we just have a quick slide for our references if you care to go and dig any further into some of the information that we use to generate this final presentation and our reports. And we'd just like to give everybody a quick thank you and really appreciate you tuning in to our final presentation. Goodbye.